Have you ever wondered what makes something like a lightning bolt so powerful? That electric current ripping through the air versus something like the rubber on your shoes that keeps you, totally safe from electric shock.
Right. Yeah, it's amazing how some things can just conduct electricity so well and others just completely block it.
It is. And it all boils down to how electrons behave at the atomic level.
Hmm.
And I don't know about you, but I'm always fascinated by getting, right to the core of how things work
Me too.
and
Absolutely.
and doing it in a way that doesn't, get bogged down in a lot of technical jargon.
Right.
So, welcome to the deep dive, where we take, complex scientific topics and break them down into easy to understand concepts.
Absolutely.
Today, we're going to be diving into the world of electron theory and chemical bonding, and we've got some great materials to guide us through this journey.
Yes, we do.
Our goal today is to really unpack why different materials have such dramatically different electrical properties.
Yeah.
Why some things are fantastic conductors while others are staunch insulators.
Exactly. And we're going to go deep. We're going to explore the tiny pathways that electrons take as they whiz around an atom. We'll look at how those atoms link up to form molecules and even how they can fall apart through processes like corrosion.
Yeah, that sounds pretty cool.
It is. It's going to be like a backstage pass to understanding the electrical nature of everything around you.
I love that backstage pass.
Yeah.
Okay, so to kick things off,
Hmm.
our materials start by talking about electron orbitals. And,
Hmm.
to get a picture of this, imagine an atom like a miniature solar system.
Okay.
Section 2.2 and figure 2.1 in our materials illustrate these orbitals as the specific paths where electrons hang out as they orbit the nucleus, kind of like planets around the sun.
Right, right.
But what's the force that keeps these negatively charged electrons tethered to the positively charged nucleus? Why don't they just fly off?
Well, that's a great question, and it's all about electrostatic attraction. You see opposite charges attract, and figure 2.1 really beautifully shows this pull between the protons in the nucleus, which have a positive charge, and the electrons, which have a negative charge.
Wow.
And it's this fundamental attraction that actually holds the whole atom together. It's the glue.
Wow, so it's like an invisible force field holding it all in place.
Exactly. And in fact, one of the questions in our materials, question number 1,
Mhm.
asks about this force, and the answer is attraction, no doubt about it.
Attraction. Okay, so now let's zoom out a little bit to the outermost reaches of this atomic solar system and talk about valence electrons.
Okay.
This is highlighted in section 2.3 and figure 2.2.
Right. And these valence electrons, they sound like they're pretty important. What makes them so special?
Oh, they are. The valence electrons are like the rock stars of the atom.
Okay.
They get to hang out in the outermost electron orbital, which we call the valence shell.
Okay.
And figure 2.2 gives us a great visual of this, showing a copper atom with its single valence electron kind of out there on its own.
And just to make sure we're all on the same page, question 2 in our materials asks for the name of these outer shell electrons.
Right.
And the correct answer is valence electrons.
Valence electrons. Got it. Okay. So now we know where these valence electrons live. But how do we convince them to actually leave their atoms and start moving, to create an electrical current?
Right. That's the key.
Yeah. Section 2.4 and figures 2.3 and 2.4 talk about freeing these electrons. It sounds like it takes a bit of effort.
It does. It does. And this is where we have to understand a principle called Coulomb's law. It's all about the relationship between electrostatic force and distance.
Okay.
So the farther away an electron is from the nucleus, the weaker the attractive force between them.
Interesting.
It's kind of like if you're holding onto a ball with a really long string.
Okay.
It's easier for someone to pull that ball away from you than if you were holding it with a short string.
Right. That makes sense.
And because valence electrons are the farthest out, they're the easiest ones to liberate.
Makes sense. And question 3 in our materials kind of reinforces this, right? It says that the strength of the electrostatic field decreases with distance.
Exactly. The answer there is B, decreases.
Decreases. Okay, so if we apply a little bit of energy, we can overcome that weaker hold on the valence electrons.
Yeah, you got it.
And figure 2.4 shows this visually with the movement of valence electrons when energy is applied.
Right.
So what's the key takeaway from that illustration?
Well, what it shows is that when you apply energy to an atom, it's not like you're targeting just one specific valence electron.
Okay.
That energy is actually distributed evenly among all the valence electrons, and that's highlighted in question 4. The answer is a evenly.
Evenly.
Okay. So when a valence electron absorbs enough of that energy, it can break free from the pull of the nucleus and potentially move to a neighboring atom. And this flow of liberated electrons is what we call an electric current.
Okay, so free-flowing valence electrons equals electricity.
Yeah.
Got it. All right. So that brings us to conductance. This is explored in section 2.5 and figures 2.5 through 2.7 and 2.9 and 2.10.
Okay.
So what exactly is conductance and what determines how well a material conducts electricity?
So conductance is simply how easily a material allows those valence electrons to move around.
Okay.
And question 5 gets right to the heart of this. It says that conductance is all about the movement of valence electrons. The answer is C, movement.
Movement.
Okay. Now, if you look at really good conductors like copper shown in figure 2.5 and aluminum in figure 2.6, you'll notice they have a relatively small number of valence electrons.
Okay.
And question 6 kind of tests us on this. It says that conductive elements typically have 1, 2, or 3 valence electrons, making them well conductive. The answer is B, conductive.
Conductive, right? So copper has 1 valence electron and aluminum has 3.
Exactly. Copper's got that one lonely valence electron. It's very loosely held, and it can easily jump to neighboring atoms when you apply an electrical potential. It's like an electrical push.
So it's almost like copper has this, spare key that's easy to grab and go.
It's a perfect analogy. And aluminum, with its 3 valence electrons, it's not quite as free as copper, but those 3 electrons are still relatively easy to dislodge and get moving.
Okay, so aluminum is still a good conductor, just not quite as good as copper.
Right. And figure 2.7 lays out the order of conductivity for us. It shows silver, then copper, then gold, and then aluminum. And question 7 checks us on this. The answer is D, silver, copper, gold, aluminum.
Silver, copper, gold, aluminum. Okay, but it's interesting, silver is the best conductor, but you don't see silver wires in your house.
That's a great point, and that's where practical considerations come into play.
Okay.
The author's comment in our materials mentions that even though silver and gold are the top conductors, they're also very expensive.
Right.
So it's not practical to use them for everyday wiring. But as figure 2.8 hints at, and even though we're not focusing on it directly today, they do have specific applications.
Okay.
Plating on electronic connectors, where you absolutely need the best possible conductivity, and you need to prevent corrosion.
So it's a trade-off between performance and cost. Okay, so we've talked about conductors. Let's flip the script now and talk about insulators, the things that resist the flow of electricity.
Okay.
Section 2.6 and figures 2.11 and 2.12 go into detail about this. So what makes an insulator so effective at blocking those electrons?
Well, the big difference here is in the number of valence electrons.
Okay.
Figure 2.11 shows that insulators typically have 6 to 8 valence electrons, and question 10 asks us about this. The answer is 8.
8, okay.
So things like wood, plastic, rubber, glass, all those common insulators, they fall into this category as shown in figures 2.11 and 2.12.
So having a nearly full or completely full outer shell of electrons acts like a barrier, prevents those electrons from escaping.
Right. It's like a really strong security system for those electrons.
I like that analogy.
With so many valence electrons tightly held by the nucleus and very few spaces to accept new electrons, it takes a huge amount of energy to free up any electrons and get them moving.
Okay, so that's why insulators are so good at resisting the flow of electricity. Now we've got this fascinating middle ground between conductors and insulators, the semiconductors.
Right.
Section 2.7 and figures 2.13 and 2.14 introduces to these. So what makes semiconductors so unique?
So semiconductors like carbon, silicon, and germanium, as shown in figures 213 and 214, they typically have 4 or 5 valence electrons, and that's highlighted in question 11. The answer is D, 4 or 5.
4 or 5, okay.
So their inherent conductivity falls somewhere between conductors and insulators.
Okay.
But what makes them really interesting is that you can actually control their electrical conductivity very precisely by adding tiny amounts of impurities, and this is a process called doping.
Doping.
Yeah, and the author's comment in figure 214 emphasizes just how important this is. This ability to fine-tune the electrical behavior of semiconductors is what makes them the building blocks of all modern electronics.
That's incredible. So just a slight variation in the number of those valence electrons can lead to such drastically different properties.
Absolutely.
We've got metals that easily conduct electricity, insulators that stubbornly resist it, and then these semiconductors that can be manipulated to create the digital world we live in.
Exactly. It's pretty mind-blowing when you think about it.
It is. All right, so let's shift gears now and talk about how atoms interact with each other through chemical bonding.
Okay.
This is covered in section 2.8 and visualized in figures 2.15, 2.17, and 2.18. So why do atoms even bother to bond in the first place, and how does this affect their electrical properties?
Well, atoms are kind of like us. They want to be in a stable and comfortable state.
Okay.
And for most atoms, this means having a full outer valence shell, which typically means having 8 electrons.
Right, like that magic number 8.
Exactly. And question 12 confirms this. The answer is D8.
8.
So chemical bonding is all about how atoms can share or transfer valence electrons to achieve this stable configuration.
Like they're teaming up to fill their outer shells.
Right. And as question 13 points out, this bonding can create a completely new molecule with its own unique electrical characteristics that might be totally different from the individual atoms that formed it. The answer is B, compound.
Compound, okay.
So, for example, look at figures 215 and 217. They show the formation of copper oxide.
Right.
You take copper, which is a fantastic conductor, and combine it with oxygen, and what do you get?
Yeah.
An insulator.
Wow, that's crazy. So it's like taking the ingredients for a delicious cake and ending up with a brick.
Exactly. Copper, with its single valence electron, wants to achieve stability.
Right.
And so it bonds with oxygen, which has 6 valence electrons.
All right.
And in doing so, the free-moving electrons that made copper so conductive are no longer readily available.
So the bonding process locks those electrons down.
Exactly. And you see a similar story with aluminum in figure 218. Aluminum, with its 3 valence electrons, bonds with oxygen to form aluminum oxide, which is also an insulator.
So this brings us to rust and corrosion.
Yeah.
Right, the real-world consequences of these chemical reactions.
Exactly. This is covered in section 2.8b, and questions 14 through 16 really get into the nitty-gritty of this.
Okay.
So rust on iron or corrosion on metals in general is basically a chemical reaction between the metal and things in the environment, like water and oxygen.
Right.
And figure 216 shows us this visually.
Okay.
And question 14 asks us to identify this process, and the answer is B, corrosion.
Corrosion, okay.
So when copper is exposed to the environment, it reacts with oxygen to form that copper oxide, the same insulating compound we just talked about. And question 15 asks us to identify the metal in this case. And of course, the answer is B, copper.
Copper, okay.
And we see the same thing happening with aluminum. When it's exposed to the elements, it forms aluminum oxide. And question 16 checks us on this. The answer is aluminum.
Aluminum, so both copper and aluminum, these great conductors can react with oxygen to form these insulating oxide layers.
Right. And while this oxide layer can sometimes act as a protective barrier against further corrosion, it's definitely not a good thing if you're relying on that metal for electrical conductivity.
Right, like those corroded battery terminals you always see.
Exactly. That corrosion is an oxide layer that's hindering the flow of electrons.
Okay, so one last thing before we wrap up. Let's circle back to those all-important valence electrons and the energy needed to set them free.
Okay.
We know from question 8 that copper has 1 valence electron, and that single electron is pretty easy to liberate with a little bit of energy.
Absolutely. With only 1 valence electron to focus on, the energy you apply to a copper atom is primarily concentrated on that single electron, making it much more likely to gain enough energy to break free from the nucleus and become a free charge carrier.
And for aluminum, question 9 tells us it has 3 valence electrons. So now the same amount of energy is spread out among 3 potential escapees.
Right. And while each of those 3 valence electrons in aluminum can still gain enough energy to break free and contribute to conductivity, the fact that the energy is distributed means that it might take a bit more energy to free a single electron in aluminum compared to copper.
Okay, so it's a bit of a tug of war.
You could say that.
All right, so to sum up our deep dive today, we've journeyed from the heart of the atom to its outer shell. We've seen how electron orbitals, and especially those valence electrons, determine whether a material will be a good conductor, a good insulator, or somewhere in between.
Yes.
And we've explored how atoms bond with each other to achieve stability, and how those bonds can sometimes create compounds with entirely different electrical properties, sometimes leading to things like corrosion.
Absolutely. And by understanding these fundamental concepts that our materials have laid out for us, you gain a whole new appreciation for how the materials around us behave.
It's true, from the circuits in your phone to the power lines that bring electricity to your house.
Exactly. It's all about those electrons.
So it really makes you wonder, with this knowledge of how electrons behave and how atoms interact, what kind of incredible new materials could we create in the future?
Right.
What kind of technological leaps could be possible if we could really manipulate these fundamental forces in new and innovative ways? It's definitely something to think about.
It is. It's an exciting time to be in materials science, that's for sure.
Absolutely. All right, that's it for the deep dive today. Thanks for joining us.
Thanks for having me.
We'll see you next time.
Bye.